And that is contrary to what seems to have been going on most of the term, at least for the last several weeks. Last week, I had a doctor's appointment. Last Friday, I had a doctor's appointment. Friday before that, I think I was at, and I had an infusion. The Friday before that, I was at professional meetings. The Friday before that, I actually was in the Birmingham campus, you know. But then the 3 Fridays before that, I was in infusion. So it's been almost 2 months, and I've only been a month, or close to 2 months, and I haven't been to the Birmingham campus once. But this Friday, I will be there. Knock on wood, you know, nothing goes wrong. I should be there at 7:45 to 11:45. Now, I saw an email saying something about a meeting on Friday that's mandatory. But the email didn't say what day or time. It was a reminder type thing, but they didn't have the attachment on it, so I couldn't see the dates and time. Now, I've got to go back and see if I can find the original email to determine that. So I may be in meetings. I will be in meetings part of Friday. I just don't know which part. So if you need to see me Friday, I should be on campus, but there will be some time. They usually don't call meetings early, so if you catch me early, I'll be in the office. All right, any questions on anything we've done so far? Okay, let's do a quick recap of where we are and where we're heading. We're in Chapter 2, Motion. You've done Chapter 1 and its lab, and you've done the first 2 labs in Chapter 2. I'm thinking and hoping and planning that we should pretty close to finish the chapter in the next, well, what we have left is the 2.5 hours, okay? If we do finish the chapter, then Thursday we should have the test on Chapter 2. If we don't finish the chapter, then we'll finish it on Thursday and have the test on next, well, bad news, folks. Sort of a bad news, good news situation. The good news is that next week is spring break week. The bad news is we won't be meeting. Sorry. Get over it. Hey! Okay. All right. So, yeah, it'll be the following Tuesday. Kind of be a little bit better, I would think, to go on and get the test knocked out Thursday if we could. So if we can finish the chapter today, then we will have the test on Thursday. And again, the test will be the last 30 minutes of the period. We might, I think we'll get far enough along. Gary's here. Far enough along Thursday, if we do get started in Chapter 3, I think we'll get far enough along to have the lab, so it'll be 2 hours class, 2 hours lab, 30 minutes in for the test. Courtney's here. Okay. All right. Anyone else come in since I called roll? So let's get moving, see if we can finish Chapter 2, and then at 3:45 we'll get ready on the lab. This time the lab is going to be down in 259. I set up as much as I could, almost as much as I could before class. That's why I didn't have much time for lunch. Another instructor needed something today and had to have it, and I was going to be in here until 5:45, so I had to get it done between my 10:45 and lunch. So I had that to take care of, and then had to set up as much of the lab as I could. I got copies to the copy room, but I haven't picked them up yet, so I'll get that. So hopefully, and today's lab is the shortest paper-wise. It's just 2 pages, and it's not very long time-wise either. So I have a feeling, sorry about this, that I may cheat you out of some of your tuition dollars today, so, but get over it. Okay. All right. Where we left off last time, where we were talking about weight and mass, we talked about it but ran out of time before we had a chance to do example 210 on page 44. So any questions before we hit this? Okay. All right. Alexis, right? All right. Anyone else come in, Sister Caldwell? All right. Now, thought they were going to give me some more white space here, but they haven't. But we'll go on and use this. I think we have room to write on it here. The question. What's that? This is on page 44, very bottom of the right-hand column on page 44. It says, what is the weight of a 60.0 kilogram person on the surface of the earth? Okay? What formula might you use? Yeah, there it is right there. Weight is equal to mass times the acceleration due to gravity. Good eyes there. Okay? Now, so we're looking for weight. Let me get my pen activated. Okay. We're looking for weight. That's the unknown here. What is the mass?
60.
Okay, the mass is 60.0 kilograms. And what is G? G, what's G? Yes, since we're in the metric or SI units, that would be 9.8 units. Units. Okay, not mass. Meters, units per second squared. That's an acceleration due to gravity. Okay? And actually, I think this book uses 9.80. No, they don't. They use 9.8. Okay? Because they only use, I'm teaching from a physics book that uses 9.80, another class. So it's 9.8 meters per second squared. Okay? So what we do is fill in the mass, 60.0 kilograms, times 9.8 meters per second squared. And what's that weight? Well, 0 goes out. 6 times 8 is 48. Carry a 4, 54, 58. Okay? What units? Kilogram, meter per second squared. And what is a kilogram meter per second squared? What? A Newton. Now, because you only have 2 significant digits there, they're only going to count over 1, 2 significant digits. Look to the right. That's an 8. It's greater than 5. So round up the first 8 and make it 590 newtons. And that's the answer they give in the book. Now, I'm not going to object if you do 588. That's close enough to 590. I'm all right with it. Okay, see how that works? Now, this formula, remember, is a net force formula, where this is the net force acting on an object, the mass of the object, and the acceleration of the object. It's just the forms are so similar. The weight of an object, which is a force, but not the net force generally, is the mass times the acceleration due to gravity, not the acceleration of the body, the acceleration due to gravity. So this is one of the component forces. This is the formula we use for the entire net force acting on an object, and that's what gives it an acceleration.
What was the answer down there?
What's that?
What was the answer to that? That 59?
The answer here,
Yes.
590. Yeah. Because we only have 2 significant digits here, we can only have 2 there, so we round that 8 up to a 9 to make it 590. It's not a very big deal, but the book sometimes pays attention to it and sometimes doesn't. Okay? Now, with that done, this same 60 kilogram person has now gone to the moon. Okay? Become an astronaut, gone to the moon. and finds out he or she only weighs 100 newtons on the moon. So the weight on the moon is 100.0 newtons. Okay? The question now, what is the acceleration of gravity on the moon? They still have the same mass, which is 60.0 kilograms. But the question is, what is G for the moon? That's the unknown here. I'll guarantee you, it's different from that on Earth. They weighed 590 on Earth, only 100 on the moon. Same person, same mass, same everything. So the acceleration due to gravity must be less. How do we figure that? Say again? Divide what? Okay, you divide 100.0, but I wouldn't use newtons. I would use the basic units. What are they? Kilogram, meters per second squared. Divide that by 60.0 kilograms. Okay? Notice the kilograms go out, okay? Cancel out. And what's 100 divided by 60? Well, actually, you can wipe out zeros here and here. And 10 divided by 6 is? Second? 1.6 something, isn't it? 1.667. Okay, so that's about 1.67, and that's meters per second squared. That's a great unit for an acceleration, right? Meters per second squared. Now, notice that since we have 4 significant digits here, but only 3 there, we could give that answer to 3 significant digits. We have enough to justify that. We didn't down there, we're limited to 2, but up there we can do 3. So Josh is here. All right, anyone else come in since I called roll? All right. So any questions on weight and mass? Sorry. Okay. So if there are no questions, we'll move to the next subtopic, and this is Newton's third law of motion. Someone remind me, what was the first law? The what? Yeah, the law of inertia, saying that an object in whatever state of motion it has, at rest, stays at rest. In motion, stays in motion, constant speed, same direction, unless acted on by an unbalanced force. So that's the first law, law of inertia. What's the second law? There's one little formula that sums it up. Say again? That's not a formula, it's a topic. This sums it up. Force is equal mass times acceleration. If there is a net force acting on an object, if there's some net force acting on the object will change its motion, meaning accelerate. Change its velocity, accelerate. And that's the formula that says it. If there's a net force acting on an object, it's going to have an acceleration. Or vice versa, if an object is accelerating, which could mean speeding up, slowing down, or just changing direction, there's got to be some net force acting on it. That's Newton's second law. First law, object maintains its velocity, basically. Not changing unless acted on by an unbalanced force. Second law says, well, if there is an unbalanced force, it's got to accelerate. The velocity changes, either in speed or in direction or both. So we're ready for the third law. Okay? Now, this third law is a little different in a couple of ways. The source of the forces, has to be some other object. Okay? That probably was true in the other two, but we didn't really worry about the other objects. If I push on this desk, okay, and I'm pushing, my finger's turning red, I'm pushing, guess what? The desk pushed back on me, right? And basically what that's saying, the third law relates to forces between two objects. So, basically the first and second law is only focused on the object at rest or moving, are being accelerated. This we're focused on two objects, at least two. Whenever two objects interact, the force exerted on the one object, me pushing on the desk, is equal in size, but opposite in direction to the force exerted on the other object, the desk exerting on me. Okay? Always equal in size, that's magnitude, but opposite in direction. Remember, forces are vector quantities. Okay? We'll go through a couple of examples a little bit later. That one brings one to mind. Whoa! That's all they say about Newton's third law. So I guess we will give some more examples. Okay? I thought for sure there was. Nope. Okay. Actually, momentum is closely related to the third law. And there are a couple of examples in the book. So let's do that. But while we got the football player up here, I'll give you my example of, well, that probably would be better to save that for momentum. Okay? Let me give you this one. Any of you ever been on an aluminum bass boat? Yeah, okay. And ever had a buddy that was supposed to tie it to the pier before you walked off? Okay? But, or the dock or whatever, but he didn't, and you went to step off of it. Oh, that was okay. You don't have friends like that, do you? What would happen? Second? The boat skips out and you get wet, okay? And the reason for that, your foot is exerting a force on the boat, and if the boat doesn't have anything holding it in, you're pushing the boat out when you're expecting the force to push you to the pier, okay? Or to the dock, okay? Now, I was on an aircraft carrier in the Navy my last year, and many times I stepped off the gangplank, and that goes back to momentum. We'll come to that one later. But that's an example of Newton's third law. We'll hit some others. Like I say, they are very closely related to momentum change, so we'll hit that with that one. Let's do the two examples in the text, and then we'll do it. I need some white space to work. What I think I'll do is erase these, and we'll work on this page. These formulas aren't necessarily appropriate, but whatever. So here's example 212. A 60-kilogram astronaut, boy, it must be the same one, 60.0 kilogram astronaut. What's that a measure of? Mass. That's the mass of the astronaut. Okay, mass of the astronaut. Is freely floating in space and pushes on a freely floating 120 kilogram spacecraft. So the 120 kilogram is the what? What was that? Second? No, it's not a force. Kilograms are still masses. This is just the mass of the spacecraft, not the not the person. Okay? And he pushes on that with a force of, they give you what it is, force of 30.0 newtons. So the 30.0 newtons is the force that the astronaut pushes on the spacecraft. Okay, force astronaut on spacecraft. Okay. And he does that for 1.50 seconds. Yeah. What's that a measure of? Time. Okay, very good. A. Compare the forces exerted on the astronaut and on the spacecraft. So what's the force exerted on the astronaut? Well, we've got the force exerted on the spacecraft. That was 30 newton. Astronaut pushing on the spacecraft. What is the force of the spacecraft on the astronaut? Second?
Would it not be 30?
It would be exactly 30, okay? So the force of it's also the force of the spacecraft on the astronaut, with one little exception. What? Opposite directions. Forces are vectors, so if that's a plus 30, the other one would be a minus 30. Has to be the same magnitude, but in an opposite direction. Now, we're just talking about magnitudes here, so the magnitude is still 30, but you have to know and realize it's in the opposite direction, because forces are indeed vector quantities. Okay? So that is the answer to the A part. Compare the forces. They're exactly equal, but they're in an opposite direction. Now, the B part here says, compare the acceleration of the astronaut to the acceleration of the spacecraft. So how do we get acceleration of the astronaut? What is acceleration? What would be the acceleration of the astronaut? Y'all aren't looking too carefully, are you? Yes, very good. There's a formula for it right here. Newton's second law formula. The force is mass times acceleration, so if you want acceleration, divide the force by the mass. So that'll be force divided by mass. And what was the force on the astronaut? 30.0 newtons. But let's use the fundamental units. What would they be? Kilogram. Second? Meters per second squared. Okay. Divide that by the mass of the astronaut, which is 60.0 kilograms. And notice the kilograms go out. And what do you have as the acceleration of the astronaut? 1/2 with the 0.500. 3 significant digits, so put them all in there. That had 3, that had 3. And what units? Meters per second squared. An excellent unit for an acceleration. Okay? Now you said they had equal forces. Does that mean that they have equal accelerations? Not necessarily. So let's do the acceleration of the spacecraft. What would that be? What would that be? Okay, that would be the force on the spacecraft divided by the, you told me before, the mass of the spacecraft. And the force on the spacecraft, like we said, was exactly the same, magnitude of 30, so 30.0 newtons, which are fundamental units, kilogram, meters per second squared, divided by the mass of the spacecraft, 120.0, what units? Kilograms. Again, the kilograms go out, and this gives you how much? 1/4, which is in decimal form would be 0.250. 3 significant digits. Even though the 120 had 4, the 30 only had 3. So, and that would be units of what? Meters per second squared. Great unit for an acceleration. So you see, when you had doubled the mass, you have the acceleration. Half the mass, you double the acceleration. Yeah, that's the relationship. Okay? So the forces were the same, that's the A part, and the accelerations were 0.500 meters per second squared for the astronaut, but 0.250 meters per second squared for the spacecraft. Okay, now, after the interaction and acceleration between the astronaut and spacecraft, described in example 212 that we just did, they both move away from their original positions. Okay? Now, initially, they were both at rest. They were sitting there. Astronaut pushed on the spacecraft. The astronaut went this way. The spacecraft went that way. Okay? because there's no unbalanced forces there. That's the only force going. So they both move. Okay? What is the new speed for each? This time we're looking for speed. You can think velocity if you want to, but speed. Say again?
Some speed over time.
Okay, some distance over time.
Yeah.
Yeah. Okay. So what is that formula that we might use for that? Especially since we know, remember, they gave us time, and they gave us, and we just calculated acceleration. Say again? Okay. The actual best formula is V final is equal to V initial plus AT. In other words, what was the initial speed plus how much did you speed up because of the acceleration? So yeah, his answer was right. Why? What's your initial velocity? Zero, because they were both at rest to begin with. So your AT would have been fine in this problem, but I want to give you the whole thing. So this would be V0, V initial being 0. So what is your acceleration? Now, which are we talking about? What is the new speed for each? We'll start with the astronaut, okay? The speed of the astronaut will be, what's his acceleration? Acceleration of the astronaut? That would be 0.500 meters per second squared, multiplied by what? And what time was it that they were pushing? He was pushing 1.50 seconds. Okay, very precise. Okay, well, the second cancels one of those seconds out, so you're left with 0.5 times 1.5 would be, second?
It will be 0.75.
0.75? Okay. Yeah. 0.750. What units? Meters per second. Very good. How about the velocity of the final velocity of the spacecraft? Well, again, the initial velocity is 0, so the acceleration of the spacecraft times the time. They were in contact at the same time. And this would be, what's the acceleration of the spacecraft? 250. What units? Meters per second squared times the same 1.50 seconds. And that second cancels that one of those seconds out. And what's that one? Second? Meters per second, you're right. What's the number? Anyone got a calculator?
0.375.
0.375. And if you didn't have a calculator, just a little hint here, it's exactly half of that, because this was half of that. Those two numbers were the same, so it would have to be the same. So 0.375 meters per second. Okay? And we got 0.75 meters per second for the spacecraft and 0.375 meters per second for the, 0.750 meters per second for the astronaut and 0.375 meters per second for the spacecraft. And in outer space, if they're not tethered or something together, they'll never meet again, because they just drift away, both of them going at that speed forever. Okay, so that's why when the astronauts are actually out there working on something and banging stuff, they're tied to the thing, because otherwise, if they pushed off, they can't get back. There's no paddling or anything else that will get them back. All right, so that was Newton's third law. Have to be two objects involved. Force of one on the other is equal to the other on the one, except in opposite directions. Equal in magnitude, but opposite in directions. Okay. So now we move to momentum, which is going to be the second part of today's lab. First part is going to be Newton's three laws, only we're going to deal with only two of them. And then the second part is going to deal with momentum. Now this is an important property. They say closely related to Newton's second law. I would say closely related to all of Newton's laws, and I would say even more so to Newton's third law, like I was just saying. Okay, but it is closely related to all three. Now, when Newton, I've never read Newton's Principia. Okay, one major reason: it was written in Latin. Okay, that Latin was considered the language of scholarship, and the scholars throughout the world knew Latin, and so anything they wrote, so the French could read it, everybody could read each other's because they all wrote in Latin. Okay. So I've never read Latin. It's sort of a dead language now. It was kind of a dead language then too, but it's sort of like English today. Most scientists write in English, even if they're from France or Burundi or China or wherever, because English has almost become the default language of science and just about anything. Okay, but there's some people, of course, within a country, they write in their own language, and then if they go and publish it somewhere else, they have to hire a translator. Okay. But momentum, when Newton was writing his paper here, the Principia, I don't think he necessarily taught, I don't know this for sure, but about the forces or the masses or the other things dealing with the body. He talked about the quantity of motion. The quantity of motion, which he defined to be its mass times its velocity. Didn't talk about the speeds by themselves or velocity by themselves. Probably not even that much about the mass by itself. But he talked about the quantity of motion, which now we call momentum. Why do we use a P? I have no clue. Okay? My guess is that's what it was in Latin. The first letter for it must have been a P letter or something. So that was the quantity of motion that Newton talked about. So he referenced all three of those. And if you think about, when you say the first law, you have to do all this rigmarole about the what to do if it's at rest or it's moving at a constant velocity or this, that, and the other. If you phrase it in its quantity of motion, here's how you say the first law. An object's quantity of motion does not change unless it's acted on by an unbalanced force. So maybe he did use force there. That's it. If it's at zero velocity, it stays at zero velocity. If it's at, Lauren, right? Okay. If it's at whatever quantity of motion it had, it stays at that. The velocity would have to be the same, the mass has to be the same. It doesn't change, okay? Newton's second law, okay? And this may be why they make special attention to it. What we say is force times acceleration. What Newton said, or my guess, because I haven't read it, is the time rate of change of the quantity of motion is equal to the net force. That's my guess of what he said. And here's what I say. What is time rate of change? You take the quantity and divide by time. Remember when we did distance? Divide distance by time, you got speed. Divide displacement by time, you got velocity. Divide velocity by time, you get acceleration. Anytime we come up with a reasonable value, well, let's take the time rate of change of that. We've done it 3 times, here's another time. The time rate of change of this quantity of motion, let's see what that would be. So let's take the quantity of motion and divide by time. Okay? Now, remember, mass is an invariant, or at least in Newton's day we considered it, except in nuclear explosions, which we hope not to have in this class. It's an invariant, not going to change. The velocity and the time could vary, right? So let's get those two together, and what do we have then? We have mass times velocity over time. Or I would say delta mv and delta t. So make that, because there's no change in mass over change in time. And what is change of velocity over change in time? What is change of velocity over change in time? Say again? No. Change of distance over change of time would be velocity. Say again? Acceleration, you got it. So this would be mass times acceleration. That's where you get Newton's second law. And it's much easier to say in terms of the quantity of motion. The time rate of change of quantity of motion is the net force acting on the object. Okay? That's it. You know, that's the second law. Okay? We won't do the third one now, but it's the same thing. Now, this concept, momentum, mass times velocity, includes the effect both of motion, that's the velocity, and inertia, which is related to the mass. So here, both of the concepts are brought together in his quantity of motion, or momentum, the m times v, mass times velocity. Okay? Oops, let me get my writing off of there. I forgot there was a... Okay. Now, here's that same astronaut that we had before, and the same spacecraft. 60 kilogram astronaut, 120 kilogram spacecraft. This is what I was looking for before. Velocity of this, when he pushes, remember they said a force of, what was it? 30 newtons, I believe it was. He responds with 0.75 meters per second this way, and the spacecraft resulted in a velocity of 0.375 in the opposite direction. You see the directions coming into play. So let's take a look. The resulting momentum of the astronaut would be his mass times velocity. 60 times 0.75 is 45 kilogram meter per second. And this one is its mass, 120 kilograms times 0.375 meters per second, 45 kilogram meters per second. So here we have the third law, basically says if two objects are interacting, their quantities of motion are equal to opposite. Boy, that's so simple to say that way. And so this is indeed what we've got. Now this also reflects what we call the conservation of momentum. Just like we said, mass is an invariant quantity, momentum is an invariant quantity. And that may be why Newton used it rather than velocity, because this was invariant. It did not change. Okay? Now these arrows here are could be referring to equal forces or equal momentum, because momentum is a vector force. Okay? Because velocity is a vector force. Mass is not. Mass is a scalar, but you just multiply mass times velocity, and that product is a vector quantity. Okay? So those probably, in this context, are referring to the momentum. Equal in magnitude, opposite in direction. Okay? We'll be doing that in lab today, too, so hang on to the thought. All right. And that's the figure at the bottom of page 47. And we have actually expressed the conservation of momentum, but this comes after it. Let's see if yeah, here it is. The conservation of momentum, the total momentum of a group of interacting objects remains the same in the absence of external forces. So that almost sounds like Newton's first law, in that there's no net external forces. Don't know if you ever thought about it, but astronaut pushing on the spacecraft, of course, the net momentum was conserved. But here we have the rifle firing a bullet. Ever think about momentum being conserved there? the mass of the bullet has to be pretty small, right? Multiply that by its velocity, but its velocity is huge. Okay, right? And the mass times velocity of the bullet, or the quantity of motion of the bullet, is this quantity. Now, at first, when you're holding it here before you fired it, what's the momentum of the system? 0. No velocity, big mass, but no velocity. When you fire it, a little mass comes out of here going in that direction with a certain velocity, big velocity. The rifle, though, has a momentum in this direction. Now, it has a much larger mass than the bullet, so its velocity can be a lot less. Have you ever fired a rifle? Most of you, some point or another. If you held it off your shoulder, what do you have? A big bruise on your shoulder. And depending on how powerful the rifle was, you could even have a separated shoulder, okay? Because you got a certain velocity of that fairly good sized rifle coming back at your shoulder. So what they have you do, snug it up to your shoulder. So now when you fire it, you become part of the rifle. So now your mass is even bigger. Not just that the rifle has a bigger mass than the bullet, but the rifle plus you has a pretty good mass, so your velocity back is pretty small. Okay? This is showing just for the rifle. And notice they did put the minus sign in here. The direction is opposite this. But the magnitudes of these momenta are the same. Okay. Now, other applications of this would involve, any of you ever been in a car accident? The very first one I was ever in, it was I think it was I had gone to college. I went to Georgia Tech. I think we had to be there maybe a week early, but certainly a few days early. And that Sunday night, before classes started on Monday, or before registration, I don't remember which it was, by that time the upperclassmen had come. Well, I was sort of lucky. My older brother was there 2 years ahead of me, so he knew the ropes, okay? And he had a bunch of friends there too. And I think we were playing cards or something, and they decided, let's go see this new movie that was out. I don't know if you've ever heard of it. Really a classic movie, Easy Rider. Any of you ever heard of it? Okay. Peter Fonda, I believe, and I know the other guy, and I can't think of his name now. Goodness gracious, he later became a star on his own. He was just sort of a sidekick in this one. Second? Dennis Hopper, exactly. Okay. Great movie. Okay. So we decided to go see. I was off at college first time. Never had just taken off to go see a movie whenever I wanted to. Always either had, hey, Dad, can I have the car? You know, I want to go see. Are you going to see a movie that costs a lot of? Yeah, felt pretty good. So here we went in Frank Michelle's car. We didn't have a car there. My father had driven us there and dropped off the bags, and he'd driven home. So we didn't have a car there, but Frank Michelle did, my brother's friend. It was a Z28, I think it was. Pretty nice, sporty little car back then. And so Frank wasn't real sure where the Capri Theater was, but my older brother knew. So Mike sat in the front seat, Frank was driving, and I was in the back seat. There wasn't much of a back seat there, so I was sort of sideways there, sitting in it. And we were tooling along, I don't remember which road it was. And Mike said, well, we're coming, oh, there it is. Well, Frank, he said, there it is. He turned without noticing, here's a car coming this way. And when the car came that way, Frank got just far enough in that right behind where I was sitting, the rear quarter of the car, wham, there it was. First day in Atlanta, not first day, but right before, the day before classes were to begin, or registration or whatever, here in a car accident. Didn't get to see the movie, all out there with the police. And what the police were doing, they had a measuring tape, and they were measuring the skid mark of that oncoming car. Why were they doing that? Second? Yes, to see how fast, if they could document how fast that car was going. Because the mass times velocity, momentum was equal. And that's how they could do it. Now, they had lots of other factors in there. Friction of the road, they had the dry condition. So they had all sorts of things. They weren't thinking conservation momentum, but that's what they're measuring. And actually, when you do have collisions and stuff like that, especially if it was head-on or something like this, that does come into play. They measure how far recoil and all that kind of stuff. Conservation momentum is there. Any kind of action-reaction interactions, they use conservation momentum. Okay. Moving right to impulse, but I'm pretty sure we've got here we go. Example 2.14. Not quite the bullet, and I wish I was trying to see if they did have it. They just talk about it in general like I did. They don't give actual numbers for that. God, I wish they did, but they don't. So let's do this one. We need some more white space to work on. Let's work right here, okay? Example 2.14, bottom of page 48. A 20,000 kilogram, what's that a measure of? Mass, and that's of a railroad car, rail car, okay, is coasting at 3 meters per second, okay? So I'm going to draw an ugly little picture here. I don't draw very good pictures. This will be the big old rail car here, and it's coasting along here with a velocity of 3 meters per second. Notice in this problem they're not fiddling with significant digits at all. That's why I said they're not very consistent. Sometimes they do and sometimes they don't. Okay? Coasting at 3 meters per second and the mass of 20,000 kilograms. Okay? It collides with this other rail car here. I'm going to try to draw them as similar as I can. Ooh. Not quite so similar. Okay, something like that. Now this one is also, it's identical. And let me see if I can make that look a little bit nicer. Probably, ooh, there went everything. Okay. All right. Let's just imagine those are the same. So it is also 20,000 kilograms. It's identical, except it says when it collides and couples with a second identical rail car at rest. What can you tell me about that? Second? Okay, what is 0 meters per second? Velocity. So we'll call this car A, and this will be car B. The velocity of car B. Okay? That's 0. That's initial velocity anyway. This will be initial velocity here of A, and that would be 0 meters per second. Okay? Not moving. Now it says couple, meaning they have some sort of connecting devices here in front, and when they come together, they couple. Okay? They're not bouncing off each other, they're coupling. Okay? Now, it says, what is the resulting speed of the combined cars? Can you get that? Sure you can, from conservation of momentum. What we do is take each car, calculate its momentum. When they combine, that's the momentum of the system, and then we undo it to come up with velocity. So what is the momentum of car A? Momentum of car A will be what? It's the mass of car A times velocity of car A. Okay? So that would be 20,000 kilograms times 3 meters per second. Okay, we'll assume that's to the right is positive. And what would that be? 60,000. And guess what? We don't have, it's not Newton. That would be kilogram meter per second squared. Momentum, even though that was Newton's unit of choice, you know, what did I call it? Quantity of motion. Quantity of motion. That was what he used, and then what they did was name the unit of force after him, not the unit of momentum, which I think would have been more appropriate, but they didn't, so we're stuck with having to always write it out, kilogram meter per second. Now, in the next section, next slide or two, we're going to get another name for momentum, but right now it's kilogram meter per second. So that's of object A. What is the momentum of object B? 0. So what's the total momentum of the two systems, of the two objects? 60,000 kilogram meter per second. So that is the total momentum of the system. Now, after they couple and start rolling, and they will, because this one's moving, that one's not, and they're on tracks, and the tracks are nice and level and smooth, and we're going to assume no friction, not a good thing, but about as little as you can get, and they start moving. Which way do you think they'll move? Yeah, they're going to move in that direction too, because that's where the momentum is, in that direction. And guess what momentum that's going to be? Momentum final for the system has got to be 60,000 kilogram meter per second. Okay? And what is that momentum going to be? The mass of the system times the, what is momentum? Times the velocity of the system. And we'll call this the final velocity of the system. Okay? Well, what is the mass of the system now? 40,000, because they're now one big system. So their masses add, so it'll be 40,000 kilograms times V system final. That's what we're looking for. That's the unknown. That's what we're trying to find. And this has to be equal to 60,000 kilogram meter per second. So what do you do to get V? Divide both sides by your 40,000 kilograms. Use your units as well. 40,000. Sorry, I'm running out of room. Okay? The kilograms go out. Everything goes out here except V system final. Okay? And here, the kilograms go out, so your units are left to be meters per second. Great units for velocity, right? Speed. Okay? These zeros go out, those zeros go out, these zeros go out, those go out, and 6 divided by 4 is 1.5. 1.5 meter per second. Which kind of makes sense, because initially we had 20,000 at 3 meters per second. Now we have twice the mass at half the speed, because momentum is conserved. The momentum of the system before the collision has to equal momentum of this collision after this, momentum of the system after the collision. That's why they get down there and measure. If they can determine an estimate of the momentum of the two cars before the interaction, then they measure how much they moved afterwards. They can estimate velocities. And this came out 1.5. Now here's the crazy part. They round that to 2. Ah! You know, because they only had one significant digit here. You may have only had one here too. They didn't tell you if any of those other zeros were significant. But that's not 2. It's 1.5. It's 3 halves. Okay? And this is where sometimes they get a little snaky with their insistence on units, okay? Rather than say 2, I would say 3/2, okay? Make it a fraction form and leave it like that. If they don't want 2 digits, make it 3/2. Okay. Now, make sense? Conservation momentum. Momentum coming in has to equal the same as momentum going out. All right, for me to erase this. Okay. Let's go to example 215. A student and her rowboat have a combined mass of 100 kilograms. So here's the student and her rowboat. I don't draw boats very well either. Here's the water line. Okay, and here she sits in her boat. Maybe she's standing. Let's see what she is. Standing in the motionless boat, so here she's standing in it, okay. Okay, there she is, long hair and everything, okay. There is she, but the motionless rowboat. Now what does that tell you? Say again?
0 velocity.
0 velocity. So VI for this system is 0. So what does that tell you about momentum of the system? Say again? It's what? It's got to be 0 because it's mass times velocity. So initial velocity of the system is 0. Now they did tell you their combined mass, the mass of the system was 100 kilograms. The boat plus the gal. Now she shouldn't be standing in the boat. That's not safe, okay, generally. Okay. Now what has happened, sorry about this, and it's in calm water too, so motionless boat in calm water. What's happened, she lost her oar, okay? It somehow floating off, you know, so she has no way to get back, okay? So here's what she thinks of doing. For some reason, she had a 5 kilogram rock in her pocket or in the boat or something, I don't know. So what she does, she throws the 5 kilogram rock out of the boat, out of the back of the boat, that's why I have her facing that direction, with a velocity of 5 meters per second. So she has this 5.0 kilogram rock, that's the mass of the rock, and she throws it with a velocity of 5.0 meters per second. That's velocity of the rock. Okay? Now originally it was at rest. She was at rest, the boat was at rest, they were all rested. Okay? And she throws that in that direction. What does that give the rock? Yeah. Quantity of motion. Now velocity is not conserved in general. We've seen that. No, velocity is not conserved. We need to get a conserved quantity. What quantity is conserved? Say again? Momentum. So what's the momentum of the rock once she throws it? Yeah, momentum of the rock is the mass of the rock times velocity of the rock, and that would be, what do you say? 5 times 5, 5.0 kilograms times 5.0 meters per second. So what's the momentum of the rock? Second? 25. Second? No, not 0.0. Only 2 digits, so 25. Kilogram meter per second. Got to have your units there, kilogram meter per second. So that's the momentum of the rock. Well, if initially the whole system was at rest, now you give 25 kilogram meter per second. In this way, what does that give you in that way? Equal and opposite. The boat and the gal must have 25 kilogram meter per second in the opposite directions. So here she has the rock, and she's throwing it in this direction with momentum of the rock equal 25 kilogram meter per second. That means the boat and she now have a momentum of what? I'm just going to call it the system again, of 25 kilogram meter per second. Okay? And what's their mass?
You said the total?
100 kilograms. So therefore, this 25 kilogram meter per second has to equal the mass of the boat and the passenger, 100.0 kilograms times V final. Because when she threw the rock, that gave the boat a velocity in the opposite direction. So what do we do to find out what it is? Divide both sides by 100 kilograms. Yep. Okay. So your final velocity of the system is going to be, what do you say it was? Nope. 0.25, 1/4. 0.25 meters per second. Not very fast, but guess what? Moving toward shore, if she has the boat pointed that way, and if there were no friction, which even water on the boat has some friction, so it's going to slow down, but at least it gets her closer to the shore. Okay? If there were no friction, it gets her all the way to the shore. Might take her a while, but it does get her there. So if you're ever dead in the water and you have something heavy you can throw with a fairly good velocity, throw it in the opposite direction you want it to go, you and the boat will go that way. Now, of course, unless she loses her footing and falls out of the boat, and now, that won't work very well. Okay, so 0.25 meters per second. Okay, and that's what we got. All right, any questions on momentum or conservation of momentum? We'll be seeing this again in lab today. Okay, so let's move on to impulse. An impulse has its own definition. It's a force acting on an object over some time interval. Okay? So, it would be Newton seconds, right? Force in newtons, sometimes in seconds, a Newton second. Now, what happens if you exert some force on an object over some time interval? Let's just assume it's kind of like a net force. You're going to change its velocity, change its momentum, right? So guess what? An impulse produces a change in momentum. Change in velocity, whatever its mass is, it's going to produce a change in momentum. So, and basically, if you think about this, that's exactly what we said when we were talking about Newton's second law. A net force produces a change in momentum. Oops, mv. Okay, that's what we did to start with, a change of momentum. I'm sorry, not quite right. Time rate of change of momentum. Net force is a time rate of change of momentum. Okay? That's what we said before, right? And that's how we get mass times acceleration, right? But what happens if we multiply both sides by the time interval? Then you get, I'm going to rearrange the order, net force times the time interval, and that's going to be a change of momentum, mv. So that's what we're saying here. An impulse, that's an impulse, produces a change of momentum. Okay? Now, any of you baseball players or baseball likers? Any? If you think about, not just baseball, tennis, golf, whatever, what do they tell you when you're, say, swinging the bat or the racket or whatever? Follow through, right? You get more power that way. Why? Because you have the force that you're hitting it with, and if the longer you are in contact with it, that's a greater time interval. So I've unfortunately done this too. never had played tennis. I went to a summer program and they had tennis there and I had to learn it. And your tendency is just go up there and slap at the ball, you know, and it would come off some. But if you've ever watched the pros do it, boy, Serena Williams, wow, I mean, she is firing it away at that, and her racket stays on that ball for a fairly long time, and that ball changes a lot of momentum, okay? So, an impulse produces a change of momentum. Same thing true with hitting a baseball with a bat. Follow through, you know, give a good heavy swing, hard swing, hit the ball sweet, you know, it's going to go. But there are occasions where you don't want to do that, right? Like you got a man on first with no or one out, and you're not all that consistent of a hitter. What does the coach have you do? Bunt. And how do they do the bunt? You just put it out there, and actually, as soon as it touches, you see them jerk the ball back, because you want that ball to dribble. You don't want to go out to an infielder, you know, and then they can throw out and get a double play maybe. You want it just to dribble, so they have to run in and pick it up. No way to get the guy going to second. He's already there. You can advance the run, yeah, it's a sacrifice bunt, okay? So that's that change of momentum. A small force for a small time makes a little change of momentum. Large force for a large time makes a big change of momentum, okay? Now, y'all are too young to remember this, but as Garland Corley used to say, when I was a boy child, back when I was young, the first cars that we ever owned, and they were always used cars, by the way, okay? My dad never invested in a new car. Did a new truck once, but always bought used cars. Better value, you thought, okay? So, the earliest cars I remember, I don't remember what years these would have been, late 50s, early 60s, you know. I was born in 51, so they were pretty old cars. I remember the dashboard of those things quite often had big, fancy, curved dashboards, you know, like this, but they were solid metal, okay? Solid metal, okay? They were substantial. And you know what they called the passenger seat? The death seat, okay? Because if you ever hit anything, there was nothing to stop that passenger from hitting that metal dashboard unless they happen to hit the windshield first. And either way, they're pretty badly messed up, okay? And I remember, I wish I could remember what year it was, my dad bought a Plymouth something or another, I think it was, and that was the first dashboard. Still had the metal dash, but now it had about an inch or so cushioning on the dash. Okay? Now, what was the purpose of that?
To stop the force it to stop the arm from going so fast.
Okay. Now, if you think about this, the impulse is a force times a time interval. You have a change of momentum. That's equal to a change, produces a change of momentum. So if that car is traveling at a certain speed and hits the tree or your guardrail or something else like that, it's going to have a change of momentum. A pretty significant change of momentum, okay? And if you are hitting that dashboard, solid metal dashboard, the time interval over which you're hitting that is really small, a thousandth of a second or something like that. So the force is going to be huge, huge. You said it right, the force is going to be big. Whereas if you have that padded dashboard, now you have to compress that and it sort of springs back. That may take a hundredth of a second rather than a thousandth of a second. What has that done? Same change of momentum, same car speed, same everything, except the time you're interacting with the dashboard is now 10 times as much. So what does that do with the force? 1/10 as much. Okay, still going to be pretty badly damaged, but the time interval, if that goes from a thousandth of a second to a tenth of a second, or that's 100, then 100, the force would be 1/100th what it was before. If it's 100th of a second, it would be only 1/10. The force is reduced. Okay? Now, later they came up with something else. in the next model car we bought. Anyone think of what that could have been? What?
Lap belt.
The lap belt, exactly. Now what did the lap belt do? That held you back, so if you did hit the dash, it took you longer to get there because that lap belt. But you could bend over and cut yourself in half, you would feel like, but it did slow you down, so it took more time for you to change your momentum, so therefore the force with which you hit the dash was a lot less. And then they added the shoulder strap to keep you from going forward, and that added another length of time so the force was less. Change of momentum was still the same. The car was still hitting the tree or whatever, if it's the same speed, all that. But if you could increase the time interval before you hit the dashboard, then you reduce the force with which you hit the dashboard. And then they came up with, which they have today, seat belts with lap belts. But now they have airbags. So now there's even more time interval before you. In fact, you may not hardly get to the dashboard or the steering column. So you don't get that implanted in your chest, So that's why airbags are so much safer. Now, these aren't the only things they've done. Back in those days, everything was metal, okay? Right. Chrome bumpers, everything was heavy, the engine was heavy, everything was made out of heavy steel, okay? Now, a couple of things. They weighed more, took more fuel to do them, but get up pretty good speed. Your momentum, mass times acceleration was quite large, okay? And a change of momentum hitting the tree is going to be quite large. But what was the thing? The engine compartment, they didn't want to damage the engine, so that was very rigid. You didn't want to damage your stuff you're carrying in the trunk, so that was pretty rigid. What was the canopy where the people were, that was the most collapsible thing there. And that's why you had engines coming into people's laps and that kind of stuff. Not a good thing to have. We were at a math meeting a couple years ago at Shelton State, and they had the Mercedes guy come in, and he went over this. He said after a while, they said, this is not the way to design a car. You want the rigid part to be the passenger area and let everything else collapse. And nowadays they have, the bumpers are plastic, okay? Let it collapse. Don't have it a rigid chrome bumper. Oh, you shiny and it looks nice, but that's not going to give any. The passenger part gave, okay? So they have chrome. Now, some of the bumpers actually have pistons behind them, don't they? Cylinders that push in, sort of like a shock absorber sideways. They don't have those anymore. That was a bad idea too. Yeah. But anyway, at one time they put those in too. But now everything, you want everything else to collapse and not the passenger area. Okay? Same type thing for, and nowadays you know this is happening, football helmets. I can remember seeing pictures, this wasn't me, but seeing pictures of the old-time football players. Those helmets were leather. Okay. I can't even imagine the injuries that came out of that, and possibly deaths that came out of that. So they developed better helmets. When I was in high school and stuff playing, you had the webbing here and then the metal helmet, and it was held off. And I think that's still the basic design, but boy, the players are bigger, they're faster, you have greater changes of momentum, so the impulses are far greater. So they're trying to do everything they can to minimize that so that you lengthen that time interval over which the impact occurs, impulse occurs, so that you reduce the forces. Because today, there have been enough lawsuits, and that's what drives everything, it seems like, is lawsuits, on head injuries, trying to think of the word.
Concussion.
Concussions, yeah. the concussions, and it's actually traumatic head, it's head trauma. Same thing that you have with, not as bad as you have with in wartime when your vehicle hits a IED on the road. That causes some pretty bad trauma. And if you think about it, poor Muhammad Ali, did y'all see him at the '96 Olympics when he lit the torch? He had Parkinson's really, really badly. I think he since died from it, right? Because of all the blows he took to his head. It had to have something to do with it. And a lot of these football players who had great careers back 20 years ago, they're having far more head injury per population than any other thing. So, yeah, not much you can do for them. Hopefully they're doing stuff for the younger kids now. Okay, so padding, not just for elbows, knees, but also for things. I can remember in the old days when you had a guardrail. It was solid metal there. You didn't want anyone going into the ditch. Well, that means the car gets crushed, Nowadays, those have, layers of not foam material, but rubber-like material behind it, so there's give to them. In fact, nowadays they have the wires going there, so there's give. They stretch, they break, whatever. You want them to have absorb that. Okay. And the barrels they have are not filled with sand. Well, they may have some sand in them to keep them in place, but the plastic barrels, they take the change of momentum, so the force is applied to them, not to the driver or the passenger. Now, I mentioned the '96 Olympics in Atlanta. I'm pretty sure that was the one, isn't it? The Summer Olympics where the gymnasts compete. So I'm pretty sure it was there. And the Chinese had, in women's gymnastics, it seems like they tried to get this youngest, smallest, fleetest gals they can do to run it. I mean, some of these look like kids, And this one was doing what they call the vault, running down just as fast as she possibly could down that runway and hitting a springboard and projecting into the air, coming down on a pommel horse, and doing flips and twists and turns, bouncing off that, and then stick their landing. That's what they all want to do. Well, she came down at a really, really high rate of speed and hit that thing, but I guess it was either going a little too fast or got her timing off or something, and when she came off the pommel horse, she went over there, not here. Here they had padding like crazy. And if you look at the vaults and the parallel bars and the rings for the men and all those things, they have just tons of padding under there. She missed the padding, hit the floor. Quadriplegic. Because same change of momentum she would have had had she hit the pad, but the time interval for her to stop hitting the hardwood floor in the gym, minuscule. Hitting all that padding, much greater time interval, force much less, much greater when she hit that. Broke bones all over her neck and stuff. Probably will never walk again. Pretty serious business. High jump, you see how, and especially pole vault, coming from way up there. I mean, what you see is a big pile of stuff here. What you don't see, there may be a pit under there also filled with all that stuff. That's impulse. Okay. I think this is probably about the place I did the story on the bass boat, stepping off the bass boat, as opposed to stepping off the aircraft carrier. What's the difference there? Same force that I exerted there, the bass boat scooted. What about the aircraft carrier? Yes, its mass was much greater, therefore its acceleration was almost negligible. Whereas bass boat, mass very low. My mass was more than a bass boat, and there it scoots, and I'm in the water. Okay, same type of principle there. Okay, here's what I was saying. they are saying it too. Force is time rate of change of momentum, okay? Initial momentum minus final momentum times the time interval. Multiply both sides by time interval, and you get force times time interval. That's your impulse, and that produces a change of momentum. Related. So, what's another unit for momentum? Especially if the final momentum is 0, you come to a dead stop, then it's the change of your initial momentum. So another unit you could use for momentum, rather than kilogram meter per second, you could use a Newton second. So there's another unit you can use. Same unit, Newton second and kilogram meter per second, because if you think about it, a Newton second, a Newton is a kilogram meter per second squared times a second. 1 second here counts with one of those, and there you have your kilogram meter per second, which is what we usually use for momentum. Okay? So either Newton second or kilogram meter per second will be your good units. All right. There are no examples under the impulse section, but I think I've just given you enough to make you sick. Okay, so now let's look at forces in circular motion. Okay? Now, when something going in a circle, are there any forces acting on it?
Yes.
Yes, because it's changing its velocity. The change of velocity is an acceleration. An acceleration has to be produced by force. Absolutely, it's accelerated motion, even though it may not be changing speed at all, because the direction is changing, that is that. Now that acceleration that we call that is called centripetal. You'll hear people talk about centrifugal force. That's really not really a force. Centripetal force is. Centrifugal, if you kind of cover these letters, what word do you almost see there? Put an E in there. Center seeking force. So that acceleration is always toward the center of the circle. That's why the banks at Talladega are pointing toward the inside of the curve. Okay? Centripetal acceleration is present. The centripetal force is the mass times that centripetal acceleration that must be acting on it. Okay? What we call the centrifugal force, that apparent outward tug, that's just because you're trying to maintain your momentum or your inertia and the thing doesn't front. It's not a real force. It's an apparent outward tug, but it's not really when the direction changes of the object. The centripetal force ends, that's a strange way to say it, if the centripetal force ends, okay? Now I can remember, I don't remember actually doing this as a kid, but I can imagine it easily. You know, having, say, a rock tied to a string and swinging it around my head. I know none of you ever did that, right? I don't know what seemed cool about it, but if the string ever breaks, what happens? The rock goes straight because its inertia wants it to go straight line motion. So basically that string is providing the centripetal force, pulling it inward toward you. But if that string breaks or slips out of your hand, it goes through a window. There's always a window somewhere that it's going to go through, okay? That results in your straight line motion again, okay? So, here is the illustration of that. If you have something going in circular motion, there has to be a force toward the center of that circle. Centripetal, center seeking, toward the center. The actual velocity is in that direction, okay? The force is in this direction, so guess what? There's no work being done there because force times displacement, they have to be in the same direction. So there's no work going on there, though there definitely is a force there. Seems a bit strange, but it's true. Okay? Unless it's changing speed or something like that. Okay? But the centripetal force is always toward the center. Velocity is this way, that's what keeps it moving. And guess what? That's why satellites go around the Earth, the moon goes around the Earth goes around the sun, all the other planets go around the sun. Our solar system goes around the center of the Milky Way galaxy, that great big massive black hole that's there. Everything's doing because there's a force pulling inward, gravity, and on the object. The velocity is perpendicular, approximately perpendicular to that. So we have circular motion. Now, I did want to give you this formula because, believe it or not, I have already talked about it before. Let's see if let's write it here. Remember, I don't know if any of you recall this, but I said most of the time when your independent variable is squared, you're going to have a coefficient with a 2 in the denominator. You know, 1/2, the distance is 1/2 AT squared, okay? That was Galileo's formula. Just happens that way. The 1/2 is here, the 2 is there, okay? It's from integration constant, though the book gave some other explanation, which was valid, but just not good. I said there's one place that won't be the case. Here it is. Your centripetal acceleration, which they call A sub c, is equal to v squared over r. So if you go back to this illustration, velocity squared divided by radius, that's your centripetal acceleration, v squared over r. You don't have a 1/2 in front of that. And part of the reason, and this isn't totally it, is that you see velocity is a variable, but so is the radius. So they kind of cancel each other out. But let's look at the units for that. Is that truly an acceleration? What is a velocity? Typical units for a velocity. Meters per second. Okay, that would be a velocity. But you're going to square that and divide that by a radius. And what would your radius be measured in? Meters. That would be meters as well. That's just a distance. Okay? So up top you would have a meter squared per second squared divided by meters. This meter cancels one of those out, and guess what you have? Meters per second squared. So sure enough, that is an acceleration. Centripetal acceleration. Well, then what would be your centripetal force? What is a force? Newton's second law. What is a force? Anybody? Mass times? Not velocity, that's momentum. Force is mass times acceleration, absolutely. And if that's a centripetal acceleration, that would then be a mass times velocity squared over radius. So there would be your centripetal force would be mv squared over r. Okay. And that's in your book. Those two equations are equation 210 and 211 on page 50. Okay? Now, this does have an example with it. So let me erase what I've got so far, and let's do the example. A 0.25 kilogram ball. 0.25 kilogram. What's that a measure of? That's your mass of the ball. Okay? A 0.25 kilogram ball is attached to the end of a 0.5 meter string. 0.5 meter string. What's that a measure of? What's that? That would be the radius of your motion. That's the string you're pulling, swinging around your head. Now I did think of this, and let me just do a little time out here. I do remember this one. I can remember as a kid, I was fascinated by this fact, that I can have a bucket of water here. Yeah, and swing it this way, and know that at one moment it was directly overhead and not a drop of that water landed on me. And the reason was centripetal acceleration, the velocity of the thing was there, so none of the water came out. I just found that was so cool that I could do that. I didn't slow down enough to. No. I was not that stupid. I may have been stupid, but not that. Oh, never mind. Didn't mean to say that if you had done it. Okay, never mind. Okay. All right. So the 0.5 meter is your length of your radius. It's moved in a horizontal circle. This is not the bucket of water. This is a horizontal circle at 2 meters per second. 2.0 meters per second. What's that a measure of? Say again? Is that acceleration? Velocity. There's your velocity. Exactly. Okay? The question is, what net force is needed to keep the ball in a circular path? So we're looking for the net force, which in this case is going to be a, moving in a circle, centripetal force. And what is the formula for that? I just had it up there, and I erased it. It's on page 50. V squared over r is acceleration. Multiply that by mass and you have force. V squared over r. So that would be, what's your M? 25 kilograms times, what's your V? What's your V? 2.0 meters per second, but you're going to square that, divided by say again, 0.5 meters. Okay? Okay, actually exponentiate first.
Oh yeah, square. All right, so that's going to be 4.
0.25 kilograms times 4, but don't just square the number. Square the units as well. Meter squared per second squared, divided by 0.5 meters. Okay? Now, what is 0.25 in fractions? 1/4 of 4 is 1. Okay? That numerator becomes 1 kilogram meter squared per second squared, divided by 0.5 meters. Well, first, this meter will cancel one of those out, and sure enough, what is 1 divided by a half? 1 multiplied by a half is a half. 1 divided by a half is, okay, I think in terms of food. I have a pizza. I divide it by half. How many pieces do I have? 2. 1 divided by a half is 2.
Yeah,
Okay, so that would be 2. Or you could do it this way. 1 divided by 1/2 is the same as 1 times 2 over 1. That's going to be 2. So that's going to be 2, and kilogram meter per second squared is a Newton. Kilogram meter per, that's a force, centripetal force, 2 newtons. Now I'm going to take a look at this and see. Yeah, they left it just plain 2. Now notice what they didn't do, and I encourage you not to. Even though this has 1 significant digit and the others had 2, when you multiply out, don't throw them away, okay, until the very end, then round, and that rounded to exactly. If you round off in the middle, then you get round off error. So carry the units, the digits all the way through, and then at the very end, round off to your significant digits. Okay? Now, that was example 2.16, 2.17. Suppose you make the string in example 2.16 half as long. So what's the R, I'm going to call it the new R, what's its length going to be? If you make it half as long. No, that's twice as long. Half as long. 0.75 is greater than 0.5, so that's larger. Is what? 0.25. So the new length is going to be 0.25 meters. Okay. Oh, and there they give it in the book. Ha. Okay. What force is now needed? Okay. So if you reduce the radius, what do you do to the force? Well, let's just take a look at it. Here is net force, a centripetal force. It's inversely related to the radius. So you would think if you decrease the radius, you're going to increase the force. Let's see if you do. Okay. Everything else is going to stay the same, except I'm going to erase gingerly here. Okay. Everything else is going to stay the same, except I'm going to half the radius. Make that 0.25, make that a 0.25. That's not very pretty, but I did it. So everything else came up the same. That'd be 1 kilogram meter squared per second squared divided by 0.25 meters. And again, the meter cancel one of those out. And what's 1 divided by 1/4? Okay, you just multiplied. 1 divided by 1/4. 1 divided by 1/4. 1 times. What do you do when you change division? Division and multiplication.
Oh, just look. I think it'll be 4.
4, yeah. 4 over 1. So that's going to be 4 newtons. So yeah, you half the radius, you have to do it. Now, I don't know if you've experienced this before, swinging something around with a long string, swinging it around at the same speed with a short string. You have to do a lot more work on that, okay, because you're changing the direction even faster, okay. All right, so that was 4. And then this drives me nuts, okay. Because you changed it from 0.5 to 0.25, now they can put an extra digit in there because that was your limiting number of significant digits up here. Now you've got 2, so it became 4.0 newtons here, whereas the other one's 2 newtons there. They get a little carried away, it seems like. All right, and here I'm dragging my computer off the table again with this chair. Okay, so that's forces in circular motion. Now we move to Newton's law of gravitation. How are we doing on time? 3. Yeah, we got time. I think we'll get it finished. All right. Boy, did Newton do a lot of stuff. Before Newton, of course, Galileo had come up with the law of inertia. Newton refined that and improved on it quite a bit. Okay? Came up with the other 2 laws of motion never had before. Okay? Newton, those are his Principia. He, in doing the laws of motion, had to invent a whole new, brand new mathematics, calculus, okay? So he did that. He, at the same time, came up with a first ever law of gravitation, and it works really, really well. Now, not in a quantum mechanics sense. Einstein came up with something that changed it a little bit, but on a macro scale, nothing beats it. He came up with in light, you know, he came up with determined that light was not made up of a single white color; it's made up of a spectrum. You know, he did that with his prisms, and I mean, there's just an incredible amount of stuff this one dude did that changed physics inside out, you know. And this is one more, Newton's law of gravity. He also had Newton's law of cooling. I mean, there's just tons of things he did. There weren't many things he didn't do. He was into alchemy. He was into chemistry. He was into all sorts of stuff. So Newton's law of gravitation is that it's an attractive force. Now, this is the one force, the force due to gravity, it's always attractive, as far as we can tell. In the materials we know about, it's an attractive force. Your other forces, like electromagnetic forces, they can attract or repel. 2 like poles or 2 like charges are going to push each other apart. Gravitation always is pulling together. So it's an attractive force between all masses. It doesn't matter how small. It does maybe the force is so incredibly small you can't feel it, but it's always an attractive force between any two masses. Proportional to the product of the masses, you have to multiply the masses together, and that's what it's proportional to, but inversely proportional to the separation distance, but not just the distance squared. Okay? Now, that ultimately explains where we get to G, acceleration due to gravity. We'll do that in just a minute. Not right now, but we'll do it. And this provides the centripetal force for orbital motion. Okay? Gravity. Because there's no strings connecting the sun to the earth or the moon to the earth. No strings there. It's gravity is doing that centripetal force. Okay? So, here's the moon going around the earth. Gravity, force due to gravity, the earth is pulling the moon toward the earth constantly, okay? And the moon's going in that direction, but that force pulling it in is going to make the direction of the velocity change constantly, so it keeps it in orbital motion. Now, I was reading or hearing on the radio driving in this morning that some years ago, and it doesn't seem like that long ago, the Chinese put up a space station, okay? We have the International Space Station, but they decided to launch their own. And it's about the size of a bus, okay? And they haven't been able to keep it in orbit. They didn't provide enough velocity this way to keep it, and so now the gravitational force is greater than the it's what it's supposed to be, so it is in the process of falling to the earth, spiraling in, and no one can predict right now where it's going to hit. Now, we had a space station up, I say us, I think it was largely American, maybe European some too, that did the same thing. It finally came down, I think in the Pacific or Indian Ocean, one side or other of Australia, missed the planet, the continent, thank goodness, because it was pretty expensive too. But this one is going, there's going to be some bus-sized thing falling out of the air sometime in the next year or so, and it's probably going to make a pretty big bang when it does. They hope it's going to be over water. If it's not, well, we'll see. Okay. But that's what happens if you don't have enough velocity to keep it in orbital motion. Okay? And that's all they say about gravity. Okay? I thought they would at least give you the formula. So I think they should have, but it's just not showing up. I'll give you the formula. This is Newton's law of gravity. This is equation 212 in your book on page 50. The force due to gravity, I like to put F sub G, force due to gravity, is equal to capital G, that's a constant, times the product of the masses, it said that here, mass 1 times mass 2, divided by the distance squared. Okay? Now they put the G out front, you can put it out front or not. Now this G is not the same as that G. This is capital G, this is a universal gravitational constant. It works with the sun, it works with the earth, it works with, that G only is good for the earth, okay? So this is uniform gravitational constant. Now, those people with the little thin books, which I think is most of you, but a few of you have the thicker ones. In the thicker book, your physical constants is in the front. In your thinner books, they put it somewhere near the back. There's a bunch of pages at the back that, are blank, but somewhere right before those, you'll find that universal physical constant. And if you look down here, gravitational law constant, capital G, that's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay? So that's a very, very small number. Okay? So, let's do the first example with that, example 218. And let's see if I can find a place. Okay, we'll use it here. What is the force of gravitational attraction between two 60 kilogram, that's 132 pound students? Now that's not an exact comparison. Kilograms is a measure of mass, pounds a measure of weight, so they're not doing it. Standing only 1.00 meter apart. I can stand that far 1 meter apart from Tef, and I don't think we're going to find much attraction. Yeah, okay, not saying anything about you, Tef, but yeah, it's just not going to be there. We're not going to be felt like we're, I got to fight against this gravity. No. Let's see why. What's the force of gravity? And I'm a lot more than 60 kilograms, 132 pounds by a long shot. Okay, we won't say how much so. Okay, so force due to gravitational attraction is going to be that constant that I just gave you, 6.67 times 10 to the minus 11, and the units are Newton meter squared per kilogram squared. Strange looking units, right? But then we're going to multiply that by the masses. Well, each of these masses is 60 kilograms. So 60.0 kilograms times another 60.0 kilograms divided by 1.00 meters squared. Right? Yeah. So let's see what that turns out being. Well, 60 times 60 is, let me just write those down, 6.67 times 10 to the minus 11. Let's deal with the units. This is going meter squared, cancels out that meter squared. This kilogram times kilogram cancels out kilogram squared. So that's just going to be newtons times, and we got rid of all those units. This is just 3,600, 2 zeros, okay, divided by, and 1 squared is 1, okay, 0.00, okay. Now, if you want to use scientific notation, you could, or just punch it in the calculator. Are y'all familiar with how to do scientific notation on your calculator? I'm not certain that you're going to have to use any, but in case you do you know how to do that? Okay, let me sort of explain. You have a calculator that does it. Probably do if you have a scientific calculator above. You type in 6.67. Don't do a times 10. Don't do that. Look for a key that says EE or EXP. You find that somewhere on your calculator. EE or EXP. Do you have it on yours? Or do you know it? Oh, I thought that's, you were using your phone. No, okay, I saw you turn something. Okay. All right. Do you have that key? EE or EXP? Tef? You see it?
You could just, can't you just type in negative in your exponent?
You have to be very careful with that. Okay? It's so much easier to do the EE or EXP. You found it, did you? Yeah. EE or EXP. And when you hit the EE or EXP key, you'll see 2 little blocks show up. Okay? And you type in there. Now, it depends on your calculator. Does your calculator have somewhere at the bottom a minus sign in parentheses? Or does it have a CHS or a plus minus? A little negative sign in parentheses? If you have that, you type in where you have that little block after you hit EE or EXP, negative 1, 1. If you had the plus minus key or the change sign key, CHS key, you type in the 1, 1, then you hit the plus minus. So it all depends on how old your calculator is. So it's 6.67 EE or EXP minus 11. Now that's not the subtraction key minus, that's the 1 in parentheses. Times 3,600, and then you can divide by 1 if you want to, but it's not going to change anything. What do you get from that? Have you done it? that's going to be something pretty close to 2 something, isn't it? What'd you get? Say again? 2.4 times 10 to the -7 newtons. Okay? Now, 2.4 times 10 to the -7 newtons. That would be 0.000000024. That's a pretty small number. I don't think me or any other scale I can think of is going to sense that attraction. Nowhere close. It's such a tiny number. Okay. So, let's see what they got. 2.40 times 10 to the -7. Now, they put a 0 here, and the reason they did, this was 3 significant digits, 3 significant digits, 3 significant digits, everything was 3, so they put the 2.40 times 10 to the -7. Okay. Okay. Now, I'm going to use that table in the front or back, depends on where it is, again. And this time, I'm going to erase some of this. I could leave those out, but I'll leave some of those in. Okay. All right. Oops, I erased too much. Okay. Oh, I didn't mean to erase that one. All right. I'll have to go in and fill in some that I messed up. Okay. What we're going to do now is, it's not as an example, but it's on page 51, and it takes us through how we come up with this G. Okay? So the force due to gravity on the surface of the Earth, this is the one we're used to, this is the force we call weight, that would equal mg, right? Force due to gravity, weight is mg. Okay? Now this m is your mass. Okay? G is the acceleration due to gravity. Okay? So what we're going to do here, this is going to be capital G times your mass, so this is your mass, times the mass of the Earth. Okay? That's the other mass, you know, that you're creating that, over the distance you are from the center of the Earth squared. So that's the radius of the Earth squared. All right. Now, the G is the, oh, and by the way, your mass divides out, because that's your mass over here and your mass there. So this should give you the G, the acceleration due to gravity, for the Earth, because we're using the Earth's mass and the Earth's radius. Well, the G is 6.67 times 10 to the -11 Newton meter squared per kilogram squared. Okay? Multiplied that by the mass of the Earth. Go to your table of physical constants there. Earth mass, 5.97 times 10 to the 24 kilograms. 5.97 times 10 to the 24th kilograms. Okay? Okay? Divided by the radius of the Earth. Go back to that table again and find Earth's radius, average, 6.38 times 10 to the 6th meter. 6.38 times 10 to the 6th meters, but you're going to square that. Okay? So with your calculator, now the one thing I see that I'm regretting on this, no, it's going to be okay. Okay? Is this. Okay, we'll get there. So, well, yeah. 6.67 EE or EXP negative 11. Got it? Times 5.97 EE or EXP 24. Divided by 6.38 EE or EXP 6. But while you got that on your screen, square it. Okay? and then do an equal sign. What do you get? Got a number? Oh. Anyone got a number yet? 6.67 E or EXP minus 11 times 5.97 E or EXP 24 divided by 6.38 E or EXP 6, but then square that and then hit equal. 9.70? 78. Okay, that's better. 9.78, and let's see what units we have. This meter squared cancel with that meter squared. One of these kilograms cancel with that kilogram. So the only units you got left are Newton. What is a Newton, by the way? Kilogram. No, kilogram. Meter per second squared. And you're dividing that by a kilogram. So that 9.78 meters per second squared, what does that round to? 9.8 meters per second squared. That's exactly how we got that. That shows you where it came from. Why is that the acceleration due to gravity for Earth alone? Because we use the Earth's mass and the Earth's radius. Okay? A planet with the same mass, which there aren't any, but same mass with a larger radius would have a smaller, because you're dividing by a bigger number. Or with a smaller radius, same mass would be a larger acceleration due to gravity. Or a much more massive, so you can do all sorts of configurations with that and come out with different. The moon has a much smaller mass and a smaller radius as well, so it comes out 1/6 of what it is on the Earth. Okay. All right. Now, there is a table here that's not on the slide set, so I'm sort of going to point it out to you. We talk about the astronauts when they're in space being weightless. You got to be really out in deep space to be weightless, okay? But it's so much less that they feel like they're weightless, okay? And this just basically shows what we're talking about there. If when you're on the surface of the Earth, you're about 6.4. They round this to 6.4, or 6,400 kilometers. That's this is 6.38 times 10 to the 6. Divide that by 3 and make it 10 to the 3rd. That would be kilometers, and that would be 6,400. They rounded that to 6,400. So that's on the surface of the Earth. It's about 4,000 miles, about 6,400 kilometers. So if you go another 4,000 miles above, that breaks your G down to 7.9 rather than 32 feet per second squared. Why are you putting this in U.S. customary? I'm not sure. Oh, there it is, 9.8 meters per second squared. That brings it down to 2.4 meters per second squared. So your weight, if you're 154 pounds on the Earth, you're going to be 37 pounds when you're 4,000 miles up. In other words, one more radius up. Go two more radius up, your weight is dropped from 154 to 17 pounds. Another radius up and you drop to 9.5 pounds. So you feel like you're pretty weightless. You still have some weight. 4 radii up, you're down to 6.3 pounds. 5 radii up, you're down to 4.7 pounds. So you see the early drop off is pretty great. One radius goes from 154 pounds to 37 pounds. And then the next one radius takes you in half again, approximately, 37 to 17. And then the next one is still not quite a half, a little, you have more than half. But then it falls off really quickly, and you're not doing it. But by that time, you feel pretty weightless. Okay. Now, Oh, the example 2.19 was exactly the one we just did. I was saying, why are they doing that again? We had just done it. But let's now do their example 220. What would be the value of G if Earth was less dense with the same mass but double the radius? In other words, you have twice the radius of the Earth. So I'm going to erase what I need to erase, and we'll recalculate from there. The radius of the Earth is going to be half of this, which they're going to use as they use 6.4 times 10 to the minus 6, so we'll use 3.2 times 10 to the 6th, okay? So that's going to be our change here, 3.2 times 10 to the 6th, and we're going to square that. So go and punch in all the numbers you did before. Woo, goodness, I thought I was still erasing. Okay. Okay. So this time, 6.67 times 10 to the minus 11 times 5.97, same mass, EE or EXP 24, divided by 3.2 EE or EXP 6, and square that number, hit the equal sign, and what do you get? Acceleration due to gravity then is, anyone got it? 6.67 EE or EXP negative 11 times 5.97 EE or EXP 24 divided by 3.2 EE EXP 6, then square that last number, then hit your equal sign, what you get? Significantly less. Not getting it? Okay. Do it again. 6.67 EE or EXP negative 11 times 5.97 EE or EXP 24 divided by 3.2 EE or EXP 6, then square that last number, and then hit the equal sign. Still not working? Oh, what you did. Okay, 11, 24. Did you divide by 3 points? Oh, I'd answer it, and then you squared that. Yeah, what is going on? Oh, that's 24. Wait, no, wait. Because you got the right answer before doing almost the same thing. Know what's going on with the calculator. It looks like you did it right, but it comes out being 2.4. In fact, it's exactly what you would have when you doubled the radius here and you were up here. That gave you your 2.4 meters per second squared. So it dropped from 9.8 to 2.4. That's a factor of almost 4. Okay. Awfully close to 4 reduced, so we like having the Earth the way we have it. All right, let's move on to, sorry, I can't figure out what's going wrong with that. Okay, Earth satellites. Okay. Artificial satellites must travel at more than 320 kilometers above the Earth. Now, if you look at that table I was just doing, it says 320 kilometers above the Earth. Okay, that's just barely above, I mean, you're not even out there to twice the Earth's radius. That would be 6,400 kilometers. And we're talking about 320. So not very high at all, but it's still, I mean, fairly high. Must travel at least 8 kilometers per second. Now that would be about, 0.5 miles per second. Per second, okay, so that's going pretty fast. Now, if you have them there, and here's the tricky thing, you have to have them exactly the right speed, exactly the right height for them to be in what they call geosynchronous orbit. They have to stay the same place. As the Earth's turning, they stay the same place above the Earth. If you didn't, GPS doesn't work. Your satellite TVs don't work. You know, nothing would be working because you're aiming to one spot and the satellite stays there when the Earth is turning. But how does the GPS work anyway? When you beam off a satellite, all it tells you is, by the strength of the signal you get, you say you're somewhere here. And if you get a second one, you're somewhere there. Well, that puts you either there or there, okay? But a third one, and this is called triangulating, it puts you there, so now you've got to be at that point. So you've got to have a minimum of 3 signals before you can tell where you are with GPS. So that means everywhere on the Earth, they've got to have 3 satellites in a space that you can receive their signals. So that's a lot of satellites up there. That's why some portions of remote areas, I bet you Antarctica and places like that, I bet you GPS doesn't work too well there. Who's going to pay for that? Now, we do have a lot of research stations there, so maybe they did put them up there. Out in outer Siberia, I don't know if Russia bothered to put enough GPS satellites out there, but you've got to have those in order to be able to triangulate. You've got to have 3 within range of every point of the planet. Okay? All right. And that's really all they say about Earth satellites. There's more in the book. That's why I'm going to say this every chapter, if I haven't said it already. Nothing replaces reading the book. The slideshow doesn't replace it. All the little things I add don't replace it. Nothing replaces reading. The best thing you can do to do well on the test is read the chapters. Probably more than once, but at least once. Now, there are, what they say on page 53, some gravity problems. Gravity does act on astronauts in a spacecraft who are in orbit about the Earth, since gravity, and so I'll let you read that. Pretty good little blurb, okay? Then you have a nice picture there from space, a photograph of the Earth. That doesn't add a lot. Now let's move on to, and there's plenty more here, and that's a geosynchronous orbit satellite. That's what we were talking about before. Let's move on to weightlessness, and this figure is in your book. News photos sometimes show astronauts floating in the space shuttle or next to a satellite, like that guy seems to be. I guarantee you he is tethered to that satellite or that space station or whatever it is. Otherwise, one little false move and he's forever drifting away, okay? Unless they can get someone else out there to him who is tethered. Okay, they're never technically weightless, okay? But they're just so much lighter than what they were, they just seem to bounce around and be almost weightless. Okay. It's apparent weightlessness, not real weightlessness. Okay, people behind the science, some guy we've heard of before. Isaac Newton is mentioned here. Nice little article on Isaac Newton. Can this be the source for your paper?
No.
No, because this is the book. You got to get outside the book. This can lead you to an interest in looking up, but if you read this, you'll find several other names in here, I think. Archimedes, Albert Einstein, those are other people you could do. I thought they mentioned, yeah, there we go. Edmund Halley, or Halley, I think is how it is. He was an astronomer. They named the comet after him, Halley's Comet. We always say Halley's Comet, but it's really Halley's Comet. Quite an interesting little blurb here. You can read this, but then you have to go get the source for your paper somewhere else. Okay? And this actually has some sources here too, so you could actually use that source for a little bit more. Okay? But there's several things in there. Every chapter is going to have at least one of these people behind the science. There's a concepts applied, apparent weightlessness, also there. Then you hit the summary. Okay, look at this, finishing right about on time. The summary, again, let me say, read the chapter. Okay? This is sort of the summary, sort of like the Reader's Digest condensed version. Okay? You don't get the full picture. It can't possibly give you the full picture of multiple pages in less than half a page. Okay? But once you've read the chapter, the summary is pretty good to review. It focuses on some of the high points. Now notice this chapter compared to the last one. Summary of equations, we had 1 in the last chapter. 12 in this chapter, okay? So that would be one thing I would definitely have on my formula and equation sheet in case you need any of those. The key terms are probably not any more, maybe even fewer than what you had, but these are pretty important ones. They list them alphabetically, but they do put the page numbers where they were first mentioned or defined. Applying the concepts, 47 questions here, probably a few more than last time. They're all multiple choice. Their answers are given. So a great study tool is that, applying the concepts. You're not going to see the same questions, but you'll see questions about the same topic. Okay? Questions for thought, there are 12 in this chapter. Probably a few fewer than some chapters, but about normal probably. For further analysis, 6. Some chapters have fewer. This is about normal, but maybe a little more. Then the parallel exercises. I can't remember if your little thin book, if we ever found the answers to these. Ask them to put them there. I haven't found them yet, but I don't have one. I gave mine away. So look and see if you can find the answers to Group A. I know the Group B answers aren't there, but Group A is. Okay. And that takes us right up to a couple of minutes from, so let's just end it here. And what we'll do is, now this time, by the way, before you go anywhere, folks, this time the lab is not this way. It's not in 253 or 252. It's down in 259. Go down the half flight of stairs, and you have to go about halfway down the hall before the first classroom lab on the left is 259. Now, I'm thinking there's no class in there. Check and make sure. If there's no class in there, you're welcome to go in there and wait. I've got to get the lab from the copy room. I've got 1 or 2 more little things to set up for the lab.
I was trying to see, did you have an extra lab from last week?
Right. I was going to ask if you needed that. I didn't know if anyone picked up one for you or not.
No.
Okay. Projectile motion. And you can hear a lot of it on Screencast-O-Matic on YouTube, but you probably can't follow it all because I sometimes would forget to turn on my speaker again, and sometimes would forget to turn it off, so you have a lot of noise in the background. But you can get some of it. Yeah, you can use one of your. I was going to say that's the best thing.
But she'll ask you Thursday.
Okay.
Okay.
All right. All right, fantastic. Thank you.
I do the test Thursday.
Huh?
Make up test. I can make it on Thursday.
Thursday will be fine. You want to do it before class or after class?
I did before class.
Before class, that would be great. I'm in the office. I'm not always there right at 10:45 because I usually do some mess on the computer up here.
Okay.
But sometime after 10:45 until class starts at 1:15.
Okay.
Okay. Usually I'm eating lunch down there too, but that's okay. I'll give you the test, put you in a room, I'll go back and eat lunch.
That'll work. I appreciate it.
What lab you said you were going? What lab
What's
you
that?
said you were
259.
259.
Yeah.
Hey, same.
All right. I'll be a few minutes before I can get shut down here. And 2 minutes. Right? No spares? Okay. Now you'll see stationed around the room, 4 over there, 3 over here, 100-gram masses. You can read on there, it's 100-gram mass, sitting on a piece of paper. Okay, what you're supposed to do is with a quick horizontal jerk. Okay, don't pick up or down. You can't go down much, but pick horizontally. Move this out of the way and do a real quick pull of the paper horizontally. Now there's 7 stations there. Once you've done it, turn it over to somebody else. It will only take 2 or 3 tries before everybody's done it. So you do the quick jerk, pull on the paper, and then describe what happens to the mass. You can get to it now. Go for it, folks. I'll set up in front. Okay. In general, what did you find happened when you gave it a quick pull? Stayed in place. Okay. Number 2, then, what property of matter does that action demonstrate? Inertia of the mass kept it in place. Right. Okay. Now, next part of the lab, unfortunately, all of us have to fit into this little room back here. So if we'll come on back, bring your labs. Don't think we'll need a calculator right now, so you don't need that. Just bring your labs. Something to write with, too. need 2 volunteers. One here. One here. Okay, it's not too hard to stop. You volunteered first. You want to do be the first or the second? Okay. Now what we have here, if you'll notice, these are 200-gram masses hanging here by threads. Okay. Both of these are 200-gram masses. You read them and see. Okay. Now what Will is going to do on the first one here is going to take the string thread, wrap it around his finger, hold it tight, and then what you're going to do is very gradually increase the pull on the string. Just keep pulling, and if it's strong enough, after a while, one of the strings will break. What we want to do is pay attention to which one breaks first. Okay, just grab. Oh, which one broke? The top one broke. Okay, very good. All right. Well, this one has a good. Okay. All right. Was it JJ or somebody else?
Sure, we'll get out of the way.
Okay. Okay. Now what JJ's going to do is take it, wrap it around his finger like this, but he's going to give lots and lots of slack in the string, and then pull down real suddenly with one quick pull, straight down. Okay. And notice which string breaks first. Slack, slack, slack. Slack, slack. Oh, which one broke? The bottom one. Okay. Interesting. Okay. Now, here's the tough part. Using Newton's laws of motion, explain the differences in those two outcomes. Okay. One is basically defined by one law of motion, the other by another. I'll let you know there's the first and second, the third is not involved in either of these experiments. And use that to explain why we had top string breaking here, the bottom string breaking there. Any ideas? Second? Okay. What was accelerated? Huh? Okay. Yeah, possibly. But let's think in terms. Okay, what? Unbalanced force? What was that? Okay, no, yeah, they probably were both unbalanced forces. It was the actual thing. Okay, no, that would be momentum. That's more dealing with that. Okay, here's a key. We had a very quick pull here. What did you have out there? Very quick pull. Okay, and what did that have to do with? Inertia. And which one of Newton's law was sometimes called the law of inertia? What? The first law. So this one had more to deal with the first law. Okay? And in that, because the mass had so much mass here and was sitting there, a very quick pull was not going to affect this much. The inertia of the mass basically kept the top thread from even feeling the pull. It just broke at the bottom. Okay? Because of the inertia of the mass. So that was sort of the first law. Okay? So that was with the second pull, the quick jerk was Newton's first law. Okay, the law of inertia. So what would that leave this one for? Said we weren't using the third law, so second law. Good idea. Okay. Now, what does Newton's second law basically say? And it has to do with acceleration, but force. What kind of force? Okay, weight is part of it. Not velocity, that's not a force. Okay? Now let's think of this. What is Newton's second law when you say F equal ma? I always said this F stands for the net force. Very good. Is that what someone said? Okay. Net force. Now, what was the force on the bottom string? Is pull. Well, what was the force on the top string? Okay, you had the weight of the object plus its pull. So that had greater net force on the top string, less net force on the bottom string, so therefore the top was. Over here, the inertia of the mass kept going to, y'all can go back out there and finish writing there where you have all come to the right. I'll need to set up just a little bit here. I got to pick up my. I forgot to carry my computer in and turn on. Y'all got to remind me of these things. So I'm going to put this on. All right, on page 2, on the momentum part, what you found is a scale, a weighing pan if you need it, and 4 balls over there. 3 of them are large, 1 of them is a little bit smaller. Okay, over here we'll find a track, and that's what we're going to use for the most part of the lab. But what I want somebody to do, we had 2 volunteers before, so 4 more volunteers. Each one of you go over there and measure the mass of one of the balls. And keep the ball with you and bring it over here. And again, if you can keep the ball on the top this way, without it rolling off, you can measure it that way, or if you want to use weighing pan, you zero the scale with the weighing pan on it, and then measure the mass of the ball. So, however you want to do the mass, 4 people, so take the mass of those 4 balls, and call out the mass when you get it, and the rest of us will record those. Okay? 4 people. Be sure you zero the scale first. Need help? Okay. Do the mass of 1 ball. Call it out to us.
68.
Say it again.
68.
68?
Yes, sir.
Okay. Now that's 68 what? Numbers by themselves aren't good enough. Huh? Grams. Okay, but I want you to record that on your sheet in kilograms. So how many kilograms is 68 grams? How many kilograms is 68 grams?
680.
Huh?
680.
Okay. Second? Okay. Let's do 68 grams here. Okay. We'll do our conversions, and we're trying to get to kilograms. Okay. Now, first thing, okay, just one for, just do one.
I was making sure.
Okay, that's fine, that's about right. Okay, we always put the units in their place. Between grams and kilograms, one goes on top, one goes on bottom. Which one goes where? Grams where? Bottom, exactly. And kilograms are? Top, okay, that's the only place left. Now you match the numbers with the units. How many kilograms in a gram, or how many grams in a kilogram? 1,000 kilograms in a gram. Okay. Oh, wait a minute, okay. Whoa! I don't weigh as much in kilograms as I thought I did, okay? Which way is it?
Grams and kilograms.
Which way? What goes where?
In.
I need numbers. What number goes where?
1 kilogram on top and 6.
1 kilogram is 1,000 grams. You got it. A kilo means 1,000, remember? Okay. Now, when you're dividing by 1,000, what do you do with your decimal point? Which? I know, to the left. Very good. So move it 1, 2, 3 places to the left. That's how many kilograms. 0.6068. I like to put a 0 in front so you can tell where the decimal is. Okay? Kilograms. So that's what you put. Someone else measure one of the other balls. Now you take your ball. Who was that? Yeah, Trey, you got it? Okay. We're going to bring it over here. Okay. Did you zero the scale first? The reason I tell you to zero the scale, Trey may have been looking from one direction. If you're looking from the other, you need to look the same way you're going to measure the mass. How many? 28 grams? What would that be in kilograms? 0.028. So that's a little ball. Okay, you bring that one over here too. Okay, someone else do one of the other big balls. Zero your scale. What you get? Second? 70 grams, so it should be 0.07 or 0.7070 kilograms. Okay, someone do the last one. You take your ball over here. Someone do the last one. Anybody, don't be shy. Okay. What you get? 69. What would that be in kilograms? That's grams. 0.069 kilograms. Very good. Okay. Who had ball one? Oh, you had ball one. Oh.
You want to start from we can just name of any one.
What's that?
You get the name for highest solution and the highest ball one.
Yeah. You can do 1, 2, 3, 4. Any way you want. I don't care. From now on, we're talking about big balls, little balls. Okay? We got one of the big balls. Okay. You're going to take this and put it on the scale. I'll do this from now on. Okay. And I need one of the other big balls. Okay? You got one? Okay. Now, what I'm going to do here, if you read this, it says, with one large ball, these are not level, are they? Okay, that's the problem. With one large ball stationary on the track, roll another large ball toward it at the speed of about 1 meter per second. I don't know what 1 meter a second is. A meter is about that long in 1 second. It's going to be rolling along pretty fast, right? It just gives us an easy speed to measure from. Okay? Now, when it hits, I want you to notice what happens right when it hits. Okay? Because afterwards something else is going to happen. Okay? So I want you to pay attention to what happens right at the impact. What happens to the lead. And I don't care which one you call it. You can call this ball 1 and that ball 2, or this ball 1 and that ball 2. You just need to know which way you're going to do it, and then describe what happens to both balls, and that's what you're going to write in B. Okay? So what I'm going to do, now you're going to be my ball catcher, right? Okay. So this is going to be coming pretty good. I'm going to try to get down here so y'all can see. Can y'all see? Okay. He's getting scared. Okay. I'm going to roll this at some speed. I'm going to call 1 meter per second. Okay. Okay, I said y'all pay attention.
I was going fast.
Okay. This is going to be what I'm going to guess is about 1 meter per second. You ready? Pay attention to the balls right at impact. What basically happened right when they hit?
Ball one
stop.
One rolling stop.
The one that was rolling stopped.
Yeah.
And the one that was stationary picked up and rolled. Okay, now, right after that, then this will move a little bit more, and let me tell you why. What we're trying to illustrate is linear momentum. But because the roll on the track is going to roll some, it also picks up a little bit of what we call angular momentum. And that's why right after it hit, it still picked up some angular momentum and it kept rolling some. So we're trying to ignore that part. That's why I go it fast so it minimizes rolling and sort of slides down the track. It would work better if I oiled or greased the track, but then it'd be such a mess. I don't want to go with that. So anyway, you got what it was. Now, part C. Approximate the momentum of the two balls before the collision. Ball, now which one were y'all calling ball one?
Rolling ball.
The one that was rolling, okay, the one rolling. What was the initial momentum of that ball?
It was one.
Oh, wait.
It's what?
Oh, the initial?
Initial momentum, before the collision.
Oh, before the.
Okay, that's the speed, that's not a momentum. What's a momentum?
Momentum is
The amount of speed picks up.
times
It's what?
1 kilometer.
What's that?
1 kilometer per meter second.
Okay, he's up to kilometers now, so that's really moving fast, okay? Okay, what is momentum? We just did it in class. P is equal to M times V. So momentum is the mass times the velocity. And what was the velocity? 1 meter per second. And what was the mass?
68.
Yeah, 0.068 kilogram. So, or 0.069 or 0.070. They're all right around the same thing. You can take the middle one if you want to. 0.069 times 1 would be 0.069 what units? Kilogram meter per second. So the initial momentum of ball 1 was 0.069 or 068, whatever you want to say, kilogram meter per second. What was the initial momentum of ball 2? 0. It was stationary. Okay? Now, estimate what you thought, and so the initial momentum of the system of the two balls was 0.068 or 69 kilogram meter per second. Add that to 0, you get the same thing, right? Okay, now, after the collision, there's not a blank on here for this, but after the collision, what was approximately the speed of ball 1?
it was
0.
It stopped, so it was 0.
Yeah.
How about ball 2? It seemed to go at about the same speed out, so yeah, they're going to be about the same. So does it appear that the momentum was conserved? This is the E part.
Yes.
Yes, very good. Okay, this time I'm placing 2 of the larger balls on the track, and I need the third large ball. Who had it? You had the third large ball? Yeah, there it is over there. Yeah, I need it. Okay. All right. Now this time I'm going to roll this ball towards the 2 stationary balls. Okay? First I want some estimates of what you think is going to happen.
Middle one will stay still.
Middle one will not move, you say, meaning this one, and?
And one closest to us will take out.
Okay, and how about this one? It'll stop. Okay, that's the projection here. Y'all want to see if that's what we get? Now look at it right at impact and see if you see it. Ready? Okay, another option is both of these are going real slow and this one's going to stop. Okay, that could happen too. Let's see. See what's going to happen? You ready? Okay. All right. Sure enough, right at impact, this one stayed still like you said, this one stopped, and that one was the only one that took off.
So this is 3.
Okay.
So we using it about 3 to 1.
And you can name them, number them, whichever way you want, but you describe what happened.
Yeah.
This is number F.
Yeah, stop, stay.
Okay, I'll do that one in a second. Y'all got that one? Did it appear that momentum was conserved?
Yes.
Yes, because one ball was moving to begin with at one speed. At the end, 2 were stationary and 1 was moving. It's just different balls, but the momentum seems to have been conserved. Right? All right, this time I'm going to try to roll these 2 balls toward each other at about the same speed. Okay? I might need someone to cover back on this side too, because it's not going to be as bad as before, but it could be. So what is your projection of what's going to happen?
This is all half the speed. And they're going to go the opposite direction.
Okay, I heard the opposite direction. I heard half the speed. You may be right. Okay, but let's talk about this. what is the initial momentum of this system? If these two balls are about the same masses, are going about the same speed, velocity toward the center, what's going to be the initial momentum of that system? Zero, because this is positive and that's negative, or vice versa. The same momentum, but the initial momentum is zero. So what had better be the final momentum?
Stop.
So you say it's going to stop?
Yep.
That is a possibility here. But what you said before was going in opposite directions. As long as they're at the same speed, even if they're not the same as initial, they're going at the same speed as each other, your momentum will still be zero. So let's see which one is going to happen. Y'all ready? Yeah. You think it was half or about the same? About the same. Okay. We'll talk later about what kind of a collision that was. Okay. So y'all describe however it's best for you. I would have thought this bench was level, but it doesn't seem like it is. Okay. That's number G. I need the small ball.
Right here?
Huh?
Right here.
Oh, you got it. Thank you. Okay. Okay, this time I'm going to roll the small ball toward the large ball. I'm going to try to do about 1 meter per second. Any projection of what's going to happen? What's that?
I don't think the big ball's gonna move.
Not at all. And what's the small ball going to do?
Bounce back.
Bounce back this way. Okay? That's one idea. Any others? Huh? Okay. Let's just think on that one for just a moment. Yes.
Big ball's gonna move slower. The
Okay.
small one's gonna come to a stop.
Right. Now, why was that a better option than this? Initial momentum of the system is going to be in this direction. Not very big because this is a small mass, but a reasonable velocity. But this has zero momentum. So at the end, you've got to have a momentum in this direction. And if this is stopped and this one bouncing back, all your momentum is this way. And in that case, momentum wouldn't be conserved. But let's see what happens. Okay? You red-eyed? I might need someone here too. Because we said it's going to reach balance. So let's see what happens. Ready? Sure enough, this one did take off at the same speed this one had going in? No, nowhere close. Okay? And this one bounced back at the same speed it came in? No, nowhere close. So yeah, we didn't need you. Sorry. Okay? So you write that down however you want to. Do you think momentum was conserved in that case?
Yes, sir. What does that mean, actually?
Say again?
What does that mean, actually?
Okay, that means that your initial momentum and the final momentum was the same.
No.
Why not?
You could see it.
Okay. In the previous case, the big ball was there, the small ball was here. The initial momentum was not very great, okay? But it was all in the small ball. But when it hit the big ball, it gave the big ball a certain momentum, but then it had a negative momentum itself because it was coming back. So believe it or not, the big ball had more momentum at the end than the little ball did at the beginning, because the little ball not only lost momentum, reversed its momentum, so it was in the opposite direction. So the big ball wound up with more momentum than the little ball had to begin with, because you had a negative momentum this way. So yeah, it probably was pretty close to being conserved. Okay, here we have the small ball in the middle of the track. Now, it's not quite in the middle, and I'll explain this. See, this big ball rolls over that very nicely. Small ball, oops, did you hear that? Yeah, it hits down there. So I had to put the big ball on this side last time, the small ball on this side this time. So it doesn't have any interference there. Okay, what you reckon's going to happen?
Both of them go this way.
Okay, yeah, this one's gonna go that way anyway, okay. They're both gonna go that way, who's gonna be faster, slower, or whatever? Same speed, what?
Small ball and fast.
Yeah, it seems like small ball's gotta go faster, because all the momentum that starts in this ball, when it hits, it's gonna give some to that, but it's not gonna be enough to recoil this way, so it's gonna lose momentum, I think, and follow more slowly. Now, after a while, you'll see something else, the angular momentum will come into play. Pay attention to it right at collision, okay? Ready? Okay? Sure enough, the big ball did slow a little bit. The little ball took off and the big ball followed, but at a slower speed. Okay. Now, a lot of what the big ball was doing there had some angular momentum in it too. Think momentum was conserved?
Yes, sir.
Pretty good guess, yes. Especially if you count the angular momentum as well. Sad to say, that's all, folks. That's the lab for today.
We need to turn these up.
If you're ready, I can take it. Sorry, I'm cheating you out of a bunch of
It's good if it was in a dry.
Y'all found the labs helpful or not?
Yeah.
You don't want your lecture to go so far and have a... I'm just kidding. Okay, that's a good question. Okay.